Morning. Welcome to what is I think our third robot software class. Well, technically it's our fourth, but I'm also going to be going over our our third one. So basically, because I know a lot of people were missing because I made a I made a late notice call for class. But basically we gone overhead and did a very basic drive subsystem. So instead of letting you guys copy code after the short lecture, we're gonna go ahead and go to GitHub Desktop, and I'll show you guys how to pull code from there. So for now, I'm gonna go and switch to the branch that has the code that we want to look at. And so we're gonna go in and look at the notable changes. Okay, and the first thing we're gonna go in and take a look at is the left side. Okay, so there's a little bit of restructuring going on here. Okay, and I left some notes at the bottom of the robot.java page. You'll see on the bottom here, I say robot, drivetrain, motors, lifter, pneumatics, right? And so basically, last class, we went over and brainstormed a little bit of what a motor probably needs. And we decided to say, okay, well, a robot needs a drivetrain, right? It needs to be able to move around. And so that's going to require controlling motors, right? And by extension, we'll also be controlling motors via joysticks, right? So we have to take an input from joysticks. And then let's think of another subsystem, right? Because we want to separate components into subsystems to make sure our code is nice and organized. We're basically going to say, oh, we also have a lifter, like a lot of in the past several games, a lot of games where you have to lift the robot up. For example, you have to climb something, or you have to lift an object, or you have to climb up to a platform, a lifter. And let's just assume that we're not doing anything fancy and the design team has decided to use pneumatics for some sort of lifter system. Okay, so that's when we have to control pneumatics as well. So basically last class, we decided to focus on how do we write a drivetrain, right? Let's just try to make the robot move and make sure that the driver can control it with a joystick. Okay. So, and that's what we went ahead and did. So I'm going to go ahead and start by looking at the subsystems package really quickly. Okay. Remember how Java code is organized into packages, column.team213.frc, each one directory inside another. Right now, our robot.java class, as you can see, is on the same level as subsystems. So robot.java, main.java, and the subsystems directory, or what we prefer to call packages, they all belong to com.team2013.frc. Okay, so the subsystem belongs to .frc, and inside we have 3 more classes that belong to com.team2013.frc.subsystems, right? Because that's a Java packaging name system. And here we have an abstract class. And if you remember correctly from our Java software class, we use an abstract class when we want to define like the general structure of a class, and we know for sure that you're going to try to extend this class. Like you're going to make a bunch of things that are children of this abstract class, and we can use it to enforce a few functions. Now, in our normal code, because I don't want to go there yet, I don't want to overwhelm you guys with more higher level coding, because that's what we usually do. But this sort of mirrors a little bit of how we do things. So you can see here, last class, we also left a few comments, okay? So the 2 ones we're going to focus on here are read periodic inputs and write periodic outputs, okay? And let's think for a second about what read periodic inputs mean. Read as in, well, reading, obviously you're trying to get some information. Periodic as in once in a while. And inputs meaning something the user provides to the computer. And in this case, our inputs are joysticks, right? And because it's periodic, then that means we should probably call it periodically. Like we should call it once 50 times a second, as is the normal loop time for a timed robot. And so that means 50 times a second is going to be reading the position of these joysticks or the buttons, and that will let the robot more or less directly respond to what the controller or what the driver, the human controlling the robot is trying to do, right? And so in read periodic inputs, we're going to be reading joysticks, right? Because that's why I call it read inputs for a reason. And we're also going to be running in robot periodic because we want to be constantly reading the joystick information, whether it is for debugging or whatever, we're just going to read it during robot periodic. Okay, and we're making abstract, meaning whatever class it decides to, basically whenever we make a new subsystem, we'll have to implement this some way or another, right? And then we're going to take a look at write periodic outputs. Write meaning to like do something, and a periodic, also the same thing, do it over and over again really quickly on a periodic cycle. And then outputs meaning something that the computer outputs, something the computer wants to do, okay? And in this case, if remember our notes at the bottom where, okay, the drivetrain has to control motors, right? That means in write periodic outputs, we're going to be writing our output to motors. And when you start to use more commonplace like modern motors, you're technically telling the motor itself to do something. You're not driving the motor. That's a little bit different since we're stuck within the simulator right now, but we might have a chance to get to it. But for now, just think of it as we're writing to the motors. We're telling the motors to move at a certain speed, right? And in this case, if we're going to talk about the lifter, which we will later today, we're also going to be outputting pneumatics, all right? And then let's think about this for a second, right? Periodic, but you don't, if you disable the robot, you want the robot to disable, right? So when it's disabled, you want to make sure the motors aren't able to move or the pneumatics aren't able to move. So we're only going to call output motors and output pneumatics to autonomous periodic, tele-up periodic, okay? So only, and remember, autonomous periodic and tele-up periodic are when the robot is enabled and in autonomous or tele-up mode, okay? Which basically means, well, the robot's going to go move, right? So this way, we're not going to be constantly hitting the motors when the robot is disabled, okay? It just kind of like, it just, not only does it reduce CAN bus activity, it also kind of cleans up the cycle and makes sure that in the case that for some whatever reason the disabled doesn't work or whatever, the robot isn't going to go willy-nilly and we can't control it, right? So that's, I rambled on a little bit about subsystem, but this really is a core of how we're going to be managing these systems. So let's go ahead and take a look at drive.java, which we wrote last class as well. So we're going to go ahead and pay attention to the top real quick. Okay, the top is kind of important. You can see here, obviously, we're putting in the subsystems package. It's just our way of organizing code, right? We're not putting robot.java with drive.java. Okay, and we're also importing a few things because we're using libraries from WPI in order to do stuff. Okay, in this case, joystick, because we want to be able to read from the joystick, and then also PWM Talent FX, which is controlling a Talent FX motor with PWM, which is something you can directly hook up to the Arduino. Okay, and then now we're going to define our drive subsystem class. Okay, a public class drive extends subsystem, and subsystem is the abstract class that we made last time. So obviously that means we have read periodic inputs and write periodic outputs overridden, right? Because that's by the rules of extending an abstract class. And that, so basically we're going to be defining our motors at the very top. And all you need to do to define a motor within FRC is to just create a new Java object. Okay, so right now we're just doing it, we're doing it in a member variable. So when drive itself becomes initialized, when someone makes a object of drive, these are also going to initialize. And basically we're just saying, okay, let's go in and assign, let's make a variable, right? We're going to call this left motor master, right motor master. It's going to be type PWM talent FX. I'm going to create a new PWM talent FX, which we're basically saying now, okay, I want to control a talent FX with PWM on channel 0, which is where you're connected to the Arduino. Okay, so basically, this is basically just saying, okay, this is my motor. We're defining motors, okay? And you might notice here that it ends with the word master, and these two motors commented are slaves, and same with the right. That's because in a normal robot drivetrain, you don't just have one motor on the left side and one motor on the right side. You have either 2 or 3 motors on the right side. I believe Poseidon, which is our 2019 robot, had 3 motors on both sides. And then Doom Turtle from 2020 had 2 motors on each side. But the key thing is, instead of controlling 3 different motors individually and risking the motors being out of sync or whatever, maybe it'll cause them to generate an abnormal amount of back EMF or friction or whatever. And we let the motors themselves try to follow each other. And when you create drive, we'll call a few functions called .follow, which basically says if the master speed changes, then the slave's speed will change too. They'll move together. Now, that's only a feature really available in CAN motors. Oh, they all had 2 motors on each side. And which robot had 3 motors on each side? Oh, it was the t-shirt launcher, I think, had 3 motors on each side. That's right, the t-shirt launcher. Okay. Thank you for clarifying that, Grady. But in general, these built-in PWM classes provided by WPI Lib doesn't have the follow feature. That's something only found in the specific CAN libraries, such as Spark Maxis or Talent FX. They're more advanced modern motors, but for now, we're just going to deal with simple PWM. But that's it for motor initialization. Does this make sense to everybody? Yeah, don't worry, Vinny. You guys are supposed to have a subsystem folder. We're gonna be you guys will be able to copy code from GitHub soon because I don't want to spend all of class letting you guys copy and paste this code manually. Okay. And okay, so this is motor initialization. This is when we say these are the motors I want to control. You want to go over the abstract class again? Yeah, sure. So just remember, the abstract class is we're defining the behavior of a subsystem, right? Because every subsystem would decide to program for, is going to extend the subsystem.java class because we want to make sure that our code follows like a convention sort of within our own code. And basically, read periodic inputs is where we read joysticks. Okay, so as simple as this. Read periodic inputs, you read the input. You read to see if the motor's temperatures are within spec. You read the joysticks. Okay, you get the joystick values, and after that, you call write periodic outputs. You want to output the motors, and you want to output pneumatics, right? You want to update the motor speed and whatnot. So it's really these two that are key things. We read stuff, read from the user, write, we control things on the robot. Okay, does that make sense? Can everyone give me a green check mark if you guys are okay so far? The other two methods, Josh, I just kind of wrote in here because it more or less mirrors the more or less mirrors what we do in the actual code, but for now you can ignore them. But basically, realistically, if when we say undisabled, like here, I can do it right now really quickly. So here's a small trick of IntelliJ. If you right click in open spot, you can go to generate, and then you can press override methods, and it'll show you every method that you're allowed to override. And I think there's something in here. Here it is. You see this is disabled, or actually not is disabled, sorry. There should be like a disabled init method. Let's see, so you can go over it. Yeah, here you go, disabled init. Let's say I want to do disabled init, then I can say, here's my subsystem dot on disabled, right? And so for example, if I want to set the motors to 0, set the motor speed to 0 automatically when it disables, you can do that there. Anyways, I'm going to continue on. I can explain this a little bit more. It seems like most people understand everything so far, so we'll continue. And in much the same way that we've defined and we told ourselves in code where our motors are, where they exist in the physical world, and where they're hooked up electronically, we also have to declare our joysticks, okay? So I have the Wpi Lift Simulator actually running on my computer right now. And you can see here that right now it detects my joysticks, right? Right here. And it says I can drag and drop joysticks. And right now I have joystick 0, so I can assign a joystick to 0. So then when you plug in, whether it's an Xbox controller or whatever controller, it'll just be on port 0. So this is where we define our joysticks in the same way as the motor, okay? And here we're gonna find a few more things. This is something that is not unique to 2.13, but is commonly seen. It's not used by every team, but it's commonly seen in FRC, is the idea of having a demand variable. So instead of directly setting the motor speed with the methods as you read the joystick, you change the demand variable and then you update it. You'll understand this a little bit more now. But let's just think about this. Steer demand is how much we want to turn left or right. And this is going to be a value that ranges from -1 to 1 because the joystick reads from -1 to 1. Throttle demand is the same way. How fast do we want to go forward, aka how fast do we want to go backwards? And in the same way, that's going to be -1 to 1, corresponding to what the joystick says. And also 100% and -100%. And then last one is slow mode. This is just a Boolean. This is for us. So when you're driving, sometimes you want to go a little bit slower, so the driver can just hold a button. The controls will become less sensitive, and then the controller can be a little bit more accurate with its movements. And Marco, you asked why do we add demand? I want to explain this a little bit more soon, but it's just to separate the code from it separates of telling your robot that you want to move and also and then the robot will then read the demand. When you start to have subsystems that try to control each other, right? When you have systems that try to control each other or autonomous, demand helps cleans a lot of things apart because you only have one place where you tell the motor to change speed, which is within the subsystem itself. You're not in other parts of the code telling it. All you're doing is changing the demand. The part that actually changes the speed in the motor stays in the subsystem class. And it's just a way to organize the code and make sure that the code will become more reliable. It's harder to screw it up, so to speak. Okay. So, but you'll see why we use demand soon, I think. I think it'll clear up as we go. And here again, when you make a subsystem, when you decide to initialize a subsystem, we can call a few things. I haven't commented out right now because it doesn't exist with PWM. It will cause a compile error, but usually you will tell your motors to follow when you initiate the subsystem. Okay. And the next part is we're going to talk about read periodic inputs. So after I talked a whole lot about how to read joystick inputs and whatever, obviously, this is the part that actually reads the joysticks. So you can see here, we say we're assigning values to steer demand, and basically steer demand and throttle demand, the values are going to be changing 50 times a second, right? Because this is called periodically. So steer demand is equal to joystick.get raw axis 0, throttle demand is equal to joystick.get raw axis 4 times -1 times -1 to invert it, and then slow mode is equal to joystick.get raw button. Let's go ahead and go over this slowly, okay? So when we're controlling a joystick, there are these things so-called axes, okay? And axes is basically, let me see. Seems like it doesn't want to cooperate with me. Let's restart the simulator. Basically, an axis is something that can have an analog readout. Basically, it's not pure 0 and 1. It's not true or false. It can have many different values, okay? And apparently my controller is unrecognized. Let's try. There we go. Okay. You can see when I assign a joystick, the controller will let me see. So, okay. You see these axis numbers? I'm going to go ahead and move something, and you can see the axis numbers change based on where I move the joystick. You see that? And obviously different joysticks correspond to different axes. Okay, and you can see the buttons themselves. You can see the yellow boxes flashing back and forth. So basically this is how a joystick, these are how you can read the joystick values. You can read the axis value or you can read the button value. So obviously right now, I've mapped it to this specific model of controller. Every controller will often acts a little bit differently, but raw axis 0, in this case, for the steer, is this left joystick, right? You can see how when I push it all the way to the right, it's +1. When I push it all the way to the left, it's -1. So that's axis 0, okay? And then within throttle demand, you also have get raw axis, and you can see I'm using number 4. Number 4 is this one. So when I push it up, you can see throttle 4 becomes -1. When I push it to the bottom, throttle 4 becomes 1. And obviously I want 4 to be positive. It's just easier to make sense. So I'm just going to invert it here. But basically, I'm reading this raw value from -1 to 1, and from here, also a -1 to 1 number, and I'm assigning that to demand. So if throttle is at 0.5, I'm going to go forward 50%. If I go back -0.5, I'm going to go back 50% speed, okay? And the slow mode is just a Boolean, right? Joystick.get raw button will give me true or false. Is the button pressed? Is the button not pressed? And so basically, if the button is pressed, slow mode is going to become true. If it's not pressed, slow mode will be false. Okay, so these are both doubles, as you can see, and slow mode is a Boolean. Does this make sense to everybody so far? Can I get a green check mark if you guys or ask any questions? If you don't understand everything, can you guys give me a red X? Seems like most of you guys understand this so far. That's good. All right, let's go ahead and move on to write periodic outputs, okay? And there's a little bit of math going on. There's a little bit of what we do as programmers, which is trying to deal with numbers and change them and whatnot. But basically, we're going to be processing the demands now, and then we're going to go ahead and write it. We're going to go ahead and write it to the motors, okay? And before we take a look at all this whatever modifier stuff, I'm going to go ahead and focus on this dot set. If you remember correctly, we defined left motor master in the beginning of the class. We say, okay, our talent FX is going to be PWM controlled on channel 0, right? Basically, this object, PWM talent FX, has a method called dot set, and it's going to set the speed of the PWM signal, aka if we pass 1 into dot set, left motor master dot set, if we pass 1, the motor is going to go at full speed, 1 corresponding to 100%. If it's 0.5, the motor is going to go forward at 0.5 speed, aka 50%. right? Because okay, you can think about the decimal conversion between percentage and decimal. Okay, same with 0.1, negative 0.3, whatever. So by giving dot set and giving it a different value integer, double between -1 to 1, we can tell the motor to go at a different speed and in a different direction. Okay. And so let's go and talk about the math real quick, okay? Because I think you guys can understand here that here we're setting the speeds of the left and right motors. But obviously the speeds of the left and right motors are going to have to change if we want to go forward at a different speed, turn left or right at a different speed, et cetera, right? So I'm going to go over the math real quick. This is really simple and basic math, but you might be able to see this in our full-on code, which I will have you guys explore later. So here we have a double modifier. We have a double, which is 1 for now, automatically. Because when you multiply anything by 1, you keep its original value. If slow mode is true, we're going to make the modifier 0.5. Okay. And basically, this will cut the speeds in half. And it's the purpose of slow mode, right? With slow mode, you want to reduce the sensitivity. Even when you tell it to go full tilt, it's not going to go as fast. It's slow mode. It automatically makes things less sensitive, and it will let the robot, driver control a little bit more accurately. Right? So here we can see that we say in parentheses, right? Because remember our GEMDOS, parentheses first, we're going to do throttle demand plus steer demand, meaning, let's think about this. Let's say we're going full throttle right now. If I were to want to turn left, what we want to do is we want to have the left side go slower than the right side. Okay. So by doing that, the left side, if it's going left, the value is going to be -1. Right? If going left, the value is -1. So we're going to subtract 1 from the left side. Therefore, the right motor speed will be +1 and the left will be 0. You'll see this behavior in action when I go ahead and run the code. Actually, you know what? Let's go and do it right now. I forgot that I have the code running. So go ahead and pay attention to this PWM outputs. PWM0 meaning the left motor and free being the right motor. Okay. If I go full throttle forwards, you can see both of them becomes 1. Okay, that's normal. We're going full speed at 100% speed, okay? Let's say I want to turn left. I'm going to start moving the joystick left, and you can see how the left side becomes 0.6 and the right side stays 1, all the way up to until it looks like the code actually wants the motor to go completely backwards for the left side. But this way means you can turn very sharply, okay? And if I go half throttle, you can see the right side will increase in speed, the left side will decrease. If I don't have any throttle, these kind of robots, the West Coast drive, the kinds that all of our robots in 2013 has been, can turn in place. So when I do this, the left side will go backwards and the right side will go forwards. So we're going to turn in place very quickly. And that's what the purpose of the plus or minus. I'll let you guys think about this math for a second. I don't want to cumber you guys, burden you guys with this kind of math. But either way, this is the drive function. Okay, this is how we read the joystick inputs, right? If you remember correctly, we're taking steer demand and throttle demand, and we're using it to control the motors. Does this make sense to everybody? Can I get the green check mark if it makes sense? All right, awesome. I think it makes sense to everybody, most people. All right, Marco, and Marco, does it kind of make sense as to why we want to use demand?
Yeah, no, makes sense.
Right. So if in another part of the code we just want to say, okay, go full throttle, we instead of saying motor.set, we just change the demand. Okay. How can we slow the left motor down when we go left or when it's -1? Because if you think about it, right? So Grady, if you want to help explain this as well, you can too. So when we have a West Coast drive, right, we have what are basically essentially wheels on the left and right side, and then we have our motors that drive them. Okay, so these are our little motor guys. Well, if we want to go forwards, we drive both motors, aka we want the wheels on both sides to move at the same speed. That's how we go forwards, right? But if we want to turn left, that means the left wheels are going to have to go slower than the right wheels in order to curve right. And we're assuming that 1 means the motor spin forward and -1 means the motor spins backwards. So if this side, if the left side were to run at -1, right, and the right side were to run at +1, then the right side is going to go forwards and the left side is going to go backwards, and that will cause the robot to rotate leftwards. Okay. And if it's something a little bit less crazy, for example, 0.421, then the robot is actually still going to mostly go forwards, but it's just going to turn left slightly. Okay. So by changing the difference, you can change how the robot will move. I hope this kind of
Right. If it's like completely 1 and -1, then that would be like a turn in place.
Mhm.
And if that would be a
rotate, basically.
counterclockwise rotation in place. And then if you have anything less than that on either of them, it's either going to go forwards or backwards, but there will be a certain turn to it.
Right, exactly. So when it comes to West Coast Drive, this is how we manipulate the robot's movement through the field. Right, this is how we use the motors to tell a robot to go where we want. Okay. All right, let's go ahead and go into robot.java. So I've explained drive.java, but let's talk about where we actually use this to call. Because remember, this code doesn't just run itself. We have to be able to tell the code to run. If you remember correctly, robot.java is where code is actually run. So first, if we want to use an object, this is not a static class or anything, so we have to make an instance of drive. And for now, we're just going to go to the very top of robot.java, and I'm going to just make a member variable. Drive is equal to new drive. Okay, we're making a new instance of drive, and we're assigning to a variable type drive. Simple as that, right? And then, if you remember correctly, we said here, read periodic inputs has to be called in robot periodic. Write periodic output should be called an autonomous periodic. So what do? These are public functions of subsystem, meaning other code that has created an object of a subsystem, aka drive, because drive extends subsystem, can call this function. So let's go ahead and go to robot periodic. You can see here in robot periodic, drive, which is the object that I just made when the robot boots up. Every single time when the robot is alive, it's going to call read periodic inputs. So it's going to go in and read the joystick inputs. Okay, and then over in autonomous periodic, you can see here that I said drive.write periodic outputs because we want to move the motors. Also, same thing in tele periodic, we want to say drive.write periodic outputs. Okay. So robot periodic, read periodic inputs. We read the joystick always. But when the robot is enabled, aka in autonomous periodic or tele periodic, we're going to call write periodic outputs because we want to also tell the motors to run. Does this make sense to everybody? Yes or no? Basically, we're going to go to current branch. And then you can see here in the bottom, there's a button that says choose a branch to merge into Samuel. So we're going to choose another branch in this repository, 2021 tutorial bot. I'm going to tell it to merge code into our own code. So I'm going to press choose a branch, and you guys are all going to choose Samuel-teach. Okay, this is the newest code. And you see there'll be 3 conflicting files when merging Samuel-teach into Samuel. That's okay. That's very normal when you're doing GitHub. Okay. If we have stash changes, we just discard them. Yeah, go ahead and just discard them. Okay, but you can say it's unable to merge changes or present on your branch. The following files will be overwritten. And that's because I have a change here. If you have any changes on the left side, you can go select all of them. You can press right click and press discard changes. Okay. So you should have 0 change files on the left. So you're going to go ahead and try that again. Go to Samuel teach. And you can see here that it tells me there's a lot of conflicts. Okay. And you can see here, it can says open in Visual Studio Code if you want to manually go in and merge. But what we're going to do is we're just going to go ahead and just say, screw it, just copy my code. Okay, so you can see this little drop down. You can say, use the modified file from Samuel-teach. Use the added file from Samuel-teach. Okay, and then press commit merge. Okay, and then you can push origin. Does this make sense to everybody? Okay, I wanted you guys to go ahead and do it. I'll give you guys some time. I don't want to spend too much on this. If you guys don't manage to do it, if you have stash changes, discard them. Oh, how do you discard the stash changes? Let me see. Grady, if you know how to do it in GitHub Desktop, right here, if you click on the stash changes button, there should be a discard button. Yeah, use my modified file. That's right.
Wait, we merge with Samuel Teach, right?
Yeah, that's right. So click on Samuel Teach, and if it says conflicting files, use my modified files. I'll be back in about 2 minutes. I'm gonna give you guys some time to go and sort this out. Okay, I'm just gonna assume you guys don't understand anything about pistons. Okay, essentially, pistons rely on air pressure in order to, yes, you compress air to push stuff. The idea is when you smush air into like a confined space, it creates pressure. Because you're smushing more things into one space, it wants to push out back on you. Like, you know, if like you have a trash can and like it's overflowing and you want to push it in, the more you push it in, the harder it pushes back. Like the more it feels more like solid ground. That's the same concept. When you smush air into the same area, it's going to create a bunch of air pressure, and that can cause it to like push something. And in this case, with a piston, you're using air to push a piston. You're using air to push what is specifically called the piston rod. And oftentimes in robotics, we would attach the piston to a mechanism. So when the piston pushes forward, we can use that forward action to do something, or we can actually just use the piston's raw force and like, I'm not sure if the current team knows, but I know when my brother was on the Prospect Robotics, they used a piston to literally punch a ball through the air because the air has the ability to do it. And the way we use that air to our advantage is that we're able to control the flow of air. So to speak, is to use a piston, you either let air in or you let air out of the piston. Okay, when you let air rush in, the piston is going to extend outwards. When you let air out, the piston is going to go meow. It's going to go contract. Okay, let's see. Let's see if there's a piston action. Please don't give me NVA. Okay, you know what? I give up on this. Anyways, push in, push out. Okay, I hope that makes sense. See, this is the piston when it's not retracted. Okay, so it has like tank and has like a little tiny stub. And then when you put air into it, it extends out like this. Okay, so no air, air. Okay, it just goes in and out. And when you let air in, and the way we control air in and out is through the use of a solenoid. And you can think of it as like a light switch. Okay, when you have a light switch, when it's in the on position, electricity can pass through the switch, right? And when the switch is in the off position, electricity can't pass. What a solenoid does is it uses a magnet or something. It uses a magnet to basically block the passage of air in and out using a solenoid. Okay, and it's something that you can control with electricity. If you were in EP Physics 2, you would probably understand how the solenoid might be involved in that. But basically, a solenoid can be used to cut the passage of air in very much the same way that electricity works. Okay?
So
And
basically, what the solenoid does in the reference of FRC is it either says the air is going this way or the air is going that way. It's a one or the other.
yeah. Yeah,
And,
exactly.
if the air is going one way, the piston is going to be extended. If it's going the other way, it's going to be retracted.
Exactly. Yeah. And then there's one last component, or I guess we could say two. There's two more components relevant to the FRC system, which is the compressor and an air tank. Basically, the compressor is the one that actually provides air to the pneumatic system. You probably mentioned how I said that when you smush a bunch of air into a confined space, it will want to push out on it. The compressor is the one that is doing the smushing the air, basically. And what the compressor does is the compressor is going to feed smushed air, or I'm gonna call it pressurized air. I'm gonna stop using that term. It's gonna put compressed air into tanks. We're gonna store the compressed air somewhere. Okay, and let's assume a piston is initially off, right? And we have a solenoid that controls the piston. Okay, the solenoid is going to be hooked up to the tank. So the tank is going to be connected to the solenoid, and the solenoid will have two paths to go. It'll either go to the piston, okay, or it can just leak the air. Okay, or actually, I don't think I can say leak the air. Okay, let's just say that it has somewhere for the air to go. Anyways, initially the solenoid is not going to allow air to go into the piston. The piston is just going to go ahead and let its air come outwards. It's going to just leak it back into the atmosphere, depressurize. So the piston is going to be basically in an off state. It's not pushing on anything. Oh, wait, Grady, I'll go ahead and open that file so that I can show it to everybody. Let's do that. Okay, thank you, Grady. Yes. Okay, this is the what's it called? The PCM. This is the module that controls the pneumatics, and on the right are the solenoids. Okay, the solenoids are the one that actually control air. You can see there's a bunch of like tube-looking things. You can connect the pistons to that. But okay, but basically put, you need to turn on the compressor to get the compressed air, and then use the solenoid to turn the pistons on and off. To be totally honest, when you're part of the software team, you just have to more or less rely that the hardware people hook up the pneumatics correctly. So this shouldn't be something you worry too much about. But put simply, you need the compressor to get the air. So when the robot is on, we should probably run the compressor. And then we use the solenoid to turn a piston on or off. So if we want the piston to push out, we change the solenoid state. Okay. Does this sort of make sense, everybody? You guys have a general idea of what pneumatics may or may not be. The end goal is to be able to control a piston. Can I get a green check mark, yes or no? I know that was a little bit of a lot of
Yash, I'd like
information.
to answer your question. So Samuel, can you put the picture in focus?
Yes, no problem.
So basically, on the left, we have the pneumatic control module, and that's connected to the Rio. It is just getting the Samuel.
Sorry.
It's so we can plug each of the solenoids into it so that we can electronically control them.
Yep.
Then over on the right, we have the solenoids, and then it's getting it's actually getting its compressed air from the compressor and any tanks. So what's under the solenoids is just where the air is when it's traveling between the tanks and whatever. Yeah, that's a tank. You see that the thing that's clippered on it? So
Actually, this is a perfect example.
yeah, that's a perfect example. You can see that we have the compressor in the bottom left, and then we have the air tank, and then we have some pressure gauges, but then on the right we have the solenoid, and then you can see that it goes into two sides of the piston there.
Exactly.
So there's not really a whole lot of air being stored in the solenoid here. It's really just the compressor comes in, or the tanks come in one side and the air goes out the other.
Mm-hmm. You can almost think of it as like the tank and the compressor is like a battery, and then the solenoid is a switch that you can turn it on and off, and the piston is like a light bulb. If it helps to make an analogy to an electrical circuit. But yeah, this is pneumatics. Okay, I have 5 minutes, so I'm not sure if I really have time to.
I think you have time.
All right, it's just a lifter. You're right. Okay, everybody, you're gonna go and just look at me code. We're gonna go and extend subsystem, and if you guys didn't come to last class, well, you guys have the opportunity now to see how we code a subsystem. Okay, so obviously I've lifter.java, it belongs in the subsystems package. So you can see how it has the red squiggly line now, which means class lifter, I can hover over it. Class lifter must either be declared, abstract, or implement. Okay, so I got to implement methods, select both of them. So now I have my read periodic inputs and write periodic outputs. And analogous to how we did in drive.java, how at the very top we define our motors, we're going to go in and define our pistons. And I believe I just call it solenoid. Okay, because remember, we're not technically controlling a piston, we're controlling the solenoid. Okay, so we're going to call it the piston 1. Or no. Let's be a little bit more specific. Lifter piston. Okay, because this solenoid controls the lifter piston, right? And in the same way as the motor, we say new solenoid, and let's just assume we're doing it in channel 0. Okay. So it's our very first thing. As always with reperiodic, and let's assume this lifter, we're going to control it by pressing a button. Okay. And if I remember correctly, how do we do the buttons again? I'm just going to have it where when you hold down the button, it triggers and it will let go. It won't. So we're going to do the same thing as before. If you remember correctly, we had a Boolean here called slow mode. We used a button for this. All right. So we're going to go ahead and do the same thing. We're private Boolean trigger lifter, or I don't know. What's a good name for this? Lift. Okay, we're gonna call this Boolean lift. And for now, I'm just gonna go and say false. Okay, there's nothing wrong with it putting a default value on it if you want. And now remember, we're gonna go and read the button inputs. So that belongs to read periodic inputs. Now I'm gonna go ahead and make another instance of this joystick. We have a better system for doing this joystick stuff. I'll also just notice for a bit that IntelliJ set it to auto import. If you don't have to import and the thing shows up as red, you can hover over it and you can press import class. Okay. We have a better system for managing like when we initialize and whatnot the joysticks, but for now this will work. And then we're going to do the same thing here. In C and drive, we get the raw button for slow mode. I'm going to say lift is equal to joystick dot get raw button. We're going to say get raw button pressed. Okay. So when the button is pressed, it will trigger, I believe. Wait, hold on. Am I thinking about this correctly? No, I'm just going to do get raw button. And we're going to go ahead and we use buttons 1 here. I'm going to use button 0. Okay. So button 0, I believe, is B on this controller. It's this one. Okay. Now that we have our lift, we're going to go ahead and read the values of it, right? And again, in the same way, you'll see this kind of model over and over again, where you read, you set it to a variable, and then you control something. The motor, the piston is going to be in mostly the same way. Yash, it's okay. You don't have to copy it yet. In fact, you guys can just do the GitHub merge thing. As long as you guys understand this code, I think you will be fine. So we're going to go ahead and output to the piston now. And remember correctly, again, motor.set. In fact, surprise, surprise, the solenoid object has something very similar. We're going to say lifted piston dot set. And you can see when it's say dot set, IntelliJ notices that it's going to take in a Boolean, okay, if it's on or off. So all I'm going to do is pass in lift. And boom, that's all you need to control a piston. That's literally it. And in much the same way, we're going to go ahead and define the subsystem right next to drive. So we're going to call this lifter, right? And we're going to make a new instance of lifter. I could call this lifter. And you can see I have to import it. I'm going to just press Alt Enter. It's just a key, shortcut for it. If you're using the Eclipse, that is. Right? And then we're going to do the same thing. Robot periodics, say lifter.read periodic inputs. And then autonomous here, lifter.write periodic outputs. And then same thing in IntelliOut periodic. Okay. So now the lifter code will be called in robot periodic and IntelliOut periodic when needed. The code is called when needed. Okay. So yes, summary. This is it. This is all you need to control a solenoid. You can see that after we made one system, making another subsystem is actually relatively easy. All you have to do is just change the key bindings, change a few things here and there. The really great thing about coding FRC in this decade now is that so many things are standardized. The code is so well matured that it's actually very easy to get started. Does this make sense to everybody so far? Can I get a green yes or no? All right, awesome. I think most of you guys get it. Let's go ahead and run the simulator code, shall we? And I'm gonna go ahead and give you guys basically like a post-class assignment. If you guys want to challenge yourselves, you guys can use this code as reference, and you guys can try to fill out the lifter class yourself. Or if you're bored and you just want to have fun, you can go and use the GitHub merge tactic. You're gonna pull from Samuel Teach, or you're gonna merge from Samuel Teach, and you can go and run the code on your own FRC simulator. Change the buttons according to if you're using a PS4 controller or an Xbox controller. Right? Let's see. I forgot to tell it to run the GUI, so I gotta stop it. Let's go ahead and So the hard stuff is autonomous, right? To be frank, I would probably say yes, but when you want to do like really cool, complicated stuff that helps out with the driver, this stuff doesn't become easy either. So nothing comes safe, nothing comes free. If you want to do this at home, you can drag the joysticks into joystick 0 as assigned. You can see button 0, which is technically the very first one. It's actually button A, and my slow mode is B. Anyways, button A. And you can see here, we should have, let's see if, yeah, you can see how the solenoid, it detects that because we initialized the lifter class. The solenoid has been triggered. Right now, I'm pressing the buttons and whatnot. It's not doing anything to the solenoid, right? Because we're in the robot is disabled right now. That's how we designed the subsystems. When you press teleoperated, you can see that the solenoid does not change. Well, that's fabulous. Let's go and see why. Driving works. Okay, you guys got to join in on some debugging here. This is the most crummy way to debug stuff. You can print to the logs about what your code is doing. So I'm just gonna go ahead and refresh the code. And this is part of the debugging process. This always happens. You can see right now it's just saying false. Ah, you see when I'm pushing the buttons, none of the, so you can't, it tells you it does, but it's actually kind of difficult to hook it directly up. And you could, but it's just like when it's small stuff like this, you don't have to. This is the quickest, dirtiest way to do it. But when you're doing really complicated when you're trying to debug like autonomous code or something that requires the code to be jumping around, it does help a lot to use the integrated debugger. So you can see here, my main problem right now is when I'm pushing a button, nothing gets triggered. I'm gonna take a look at that. Could it be because I initialized the thing twice? Let's see. We're going to guarantee that because in Drive, we also read this, right? So we can actually go ahead and read this button. Can I press this? No. Anyways, let's go and see. Ah, so it looks like this might be caused because, oh, it's because button 0 doesn't exist. Oh, that's interesting. Let's control. Okay, I will use button 2. So be it. So I'm gonna refresh the simulator. And now, when I do this, you can see when I push down the button, the solenoid opens. When I release it, the solenoid turns off. That's all you have to do to control piston. So with this, you guys should understand how to control a motor, control piston. All right.